Hello friends, welcome to C Field Academy. This is Suraj, and today we are going to discuss about a data structure called as binary heap. So let's get started, friends. So we are going to cover the following items as part of this video. Initially we will start with a basic introduction, that is definition of what a binary heap is, then the different types of binary heaps we have, which is the max and min heap. Next we will proceed on to see how binary heap can be stored, how the data structure, how the binary heap can be stored using just a simple array. Then we will discuss the various operations that can be performed on binary heap. We'll just go through an overview of it, and we will next move on to a detailed discussion on each of these operations. First we will start with insert operation, which involves an important procedure, which is the bubble up procedure. Then we will see the extract route or the extraction procedure in the max heap, which also involves bubble down, which is the important procedure that is involved here. And notice what we have done here is we no longer discuss min heap, we just go ahead and discuss max heap. The min heap procedures or the min heap operations would be just similar, inverted with respect to the comparison. So basically wherever we have greater than, we can just replace it with less than, and then the same operations will be applicable for a min heap. So in this video we'll just concentrate on the max heap, one of the heaps which we will discuss. Next we will move on to another operation, which is the search operation, which means to find if an element exists and where it exists in the heap. Then we will move on to see how we can delete an element from the heap or the max heap. Finally, before ending, we will see how the different operations perform. So what are the complexity, time complexity for all these operations, and at the end we will have an exercise for you guys with respect to the heap. So there will be a problem given, and based on what we will cover in the video, you will have to solve the problem. Alright, cool. So let's get started with the introduction. Let's first see what a binary heap is. So a binary heap is nothing but a binary data structure with the following properties. So first, the binary tree is a complete binary tree. Now that means all the levels in the binary tree are filled except for the last level, and even in the last level the elements are filled from left to right. So this is a special kind of binary tree, and I think we discussed these details. So there is a separate video, I'll make sure to link it here, which covers a detailed description of binary trees and the different types of binary trees that are present. So I'll link it here if you want to go back and refresh what a complete binary tree is. Next we will go the next important property is basically whether it's a max heap or a min heap. So the second most important property is that each element, so if it's a max heap, each element or each node that we have will be greater than or equal to its children. And if it's a min heap, each node value is less than or equal to children. So there are two properties in summary. One is it should be a complete binary tree, and secondly the max heap or the min heap property has to be satisfied for it to be a max heap and min heap. So let's see a few examples. So here is an example. The first one, as you can see, we have a binary tree, and it's a complete binary tree, which means all the elements at all levels are filled. Level 1 is filled, level 2 is filled, level 3 is filled, only level 4 is left, and level 4 is also filled till the first 3 elements. So this is a complete binary tree, agreed. So this qualifies as a complete binary tree. Now let's see if it is a max heap or a min heap. It's actually a max heap. Why? Because notice that all the elements, for all the elements, the root or the node is greater than all the children. So let's see it one by one. Let's take the first node, which is 44. So node 44 is greater than 42 and 35. Similarly 42 is greater than 33 and 31. 35 is also greater than its children, 19 and 27. 33 is also greater than its children, which is 10 and 26, and 31 is also greater than its children, which is just 14. We don't have a right child for 31, and hence this qualifies as a max-heap. Now let's see another. Now let's take another example. So notice what happens in this this binary tree or complete binary tree. Now in this case we have no children for 31, but we have one child for 19, which is a left child for 19. So this doesn't even qualify as a complete binary tree, because remember the definition of complete binary trees: all the levels are filled from left to right, and in the bottom from all the levels are filled, and then in the bottom level nodes are filled from left to right. So since 31 doesn't have child but 19 has child, this doesn't even qualify as a complete binary tree, and hence this is not a heap. Moving forward to another example. Now let's see this this tree. Now in this binary tree we have 10 as the root, we have two more, we have its children as 14 and 19. Both of them are larger, and the children of 14 are larger than 14, children of 19 are also larger than 19, 42 and 27, and the children of 26 are also larger than 26, and children of 31 are also larger than 31. And it's a complete binary tree, which means none of the nodes is left out before before starting any other node in the lowest level. So this is actually a min-heap, in which the property of min-heap is satisfied. The property of min-heap says that every node should be less than or equal to its children. Alright, let's see another example. Now this is another example where we have 6 nodes, and we only have a left child for 44. We don't have a right child for 44, and hence this also is not a heap, because there is a node missing in level 2, and before having node in level 2 we have nodes in level 3, and hence this is also not a heap. Alright, let's see the last example finally. So this is another example. So this is more like the max-heap which we saw, but actually even this is not a max-heap. Why? Because at every place the max-heap property is satisfied. 44 is greater than its children, 35 is greater than its children, but notice 33 is not greater than its children. We have 42 which is greater than 33, and 42 is its children. Otherwise at every place max-heap property is satisfied, and it's also a complete binary tree. But this is also not a heap. This is also not a max-heap. Okay, cool. So now let's see how we can implement binary tree using a simple array data structure. Now it's actually fascinating to know that a binary heap or a tree-like structure can be easily represented using an array. So the way to do it is to just start first. So first start with the root, store the root at the first location, which means A1. The first node of the array stores the root, first element of the array stores the root. The left child is the second element, and right child the third element. Or in short, there is a pattern using which we can store the children as well as the root nodes of a binary tree. So here is a pattern. So for each node, let's say AI, the parent will be stored at, or parent will be located at AI by 2. When we say I by 2, we are using integer division, which means 3 by 2 is actually 1. We basically disregard or remove the decimal values, so we just do integer arithmetic. The left child is located at 2 star I, which means double its own index, and right child is located at 1 greater than to double its index. Now let's see an example. So here is a binary tree or a max heap which we saw before. So as we discussed, 44 is the root, so 44 will be stored at the first location over here. Now its child, which means the left child, will be stored at 2 times its location, which means it will be stored at 2. So 42 is stored at location 2. The third node, which is 35, which is the right child of 44, will be located at 2 star I plus 1 using the pattern. Now 2 star I plus 1 means 2 star 1, which is 2 plus 1 is 3. Now, hence 35 is at 3. Now similarly, other nodes, let's say children for 42 will be stored at 2 into 2, which is 4 and 5, and let's see if that is the case. So 42's child is at 33 and 31. Cool. So that is how it is. And let's also verify if the parent. Now let's take the node 2 and see where its parent will be. Now its parent will be located at I by 2, which means 2 by 2 is 1, so 1 is actually 44, so which is its parent. Let's take another example. Let's say we will take 14. Now 14 is located at 10th node, so 14's index is 10, and let's see where its parent. Now as per this formula, it should be located at 10 by 2, which is 5. So 5 is 31. So notice we have 31 is located at node 5. So this is how we can store a binary heap easily in an array and navigate to get a parent of a node or to get a left child or right child of a node. And then we can just treat the array as a binary tree and then, you know, perform our operations. Pretty cool, isn't it? Alright, now let's jump on to various operations that we can have on the binary heap data structure. So the first important operation is adding an element or inserting a new element to the heap. Now the simplest strategy here is to just add the element to the next available space, which means the bottommost and leftmost space available. And once we do that, once we add the element, because the element's value can be anything, now it will restore, it will destroy the heap property. So we have to restore the heap property, and there is a method to do that. It is called as a bubble up. We will see shortly how we can use bubble up. So basically just add the element to the heap and then restore the heap property using bubble up. Next is extract. Extract means extracting or removing the root element of the heap. So in this case, we just remove the root element of the heap, and to restore the heap property, what we do is we replace it by the last element on the last level, and then we restore the heap property using a process called as bubble down, which also we will see shortly. So extraction done, insertion done. The next operation is search. Now in terms of heaps properties, search is really not a useful feature of heap, because it ends up being the same as scanning through all the elements in an array. So but there is a specific process we can use to just avoid some cases. So what we do is we just search from the root. We will compare the root and then see if the element matches. If the element matches, we are done. We just return back the index. But otherwise what we do is we check if the element is greater than the current node, assuming it's a max heap. So which means because the root element is the maximum element in the heap, there is no point to continue further, because definitely if the element we are searching for is greater than the root itself, the element will not be there in heap. So we'll just stop. Otherwise what we do is we just recursively go through the left subtree and right subtree. And remember, this is a max heap. In a max heap, we can ignore if the searching element is greater than the root. Alright, the last one is the delete operation. So the delete operation is kind of similar to the extract operation, but what we do is this. So first of all, whichever element we want to delete, we go and remove that element. Now there will be a space vacant, so we replace that element with the last element on the last level. Once we do that, we have to restore the heap property, and in this case we have to use bubble up or bubble down depending on the case. Depending on what the value of the node is, we will have to either bubble up or bubble down to restore the heap property. Alright, cool. Now let's go ahead and see these operations in action one by one using an example. Okay, the first one is the insert property, which means adding a new element to a heap. So to add a new element to an existing min-heap, what we do is we add the element to the first available space, which means bottom level leftmost, and then we use a process called as bubble up. So the bubble up process, what it does is it's pretty simple. So when we add a new element, we just compare the added element, new added element, to its parent. Now remember, we are talking about max-heap here. Now if the new element that we added is greater than its parent, which means it's actually violating the process, so we just swap those. When we swap those, the new element will now replace its parent and parent will replace itself. So we swap, and then what happens is we compare the element again with its new parent, and we repeat this process. We repeat this process with the new parent until we see that no more swap is required. Now when we know there are no more swaps required, we have restored the heap property, and then we say we are done, the insertion process is done. So let's see it with an example now. Now here is a max-heap which we have before, and let's say we want to insert a new element which is 43. Now as we discussed, what we'll do is we'll first add it to the new location, which is the new next available location in the binary heap, complete binary tree. So we will add 43 here. So there it looks like. But then what we'll do is we have to use the bubble up process. So in bubble up, what we do is we compare the node with its parent. Now in this case 43 will be compared with this parent, and notice 43 is greater than 31. For 43 cannot be the child of 31 because it violates the heap property. So we need to swap and then move the greater element to the top. So what we do is 43 is greater than 31, due to which we swap, and then this is what we get. So 43 and 31 have been swapped, and then we have the node 43 one level up. But then we have to continue the process because we still don't know 43 is in its correct place or not. So we do the same thing again. We compare 43 with its parent. So again 43 is greater than 42, so which means 43 should be actually up and 42 should be down. So we swap again. Hence we swap, and then we will get this tree. So 43 now replaces 42, and this is the heap we have. So we have to remember, we have to continue the same process. Now the next parent of 43 is 44. So we compare 43 with 44, and 43 is less than 44, which means this satisfies heap property. So 44 will remain as the parent, and then since 43's position is defined in the heap, we say we are done. So there is no need to swap here, and then we are done. So this is the bubble up process. So let's now see the bubble up algorithm in steps, and let's discuss it quickly. So here is how the array, the tree looks like in an array representation, and here is the bubble up algorithm or the bubble up procedure. So bubble up procedure takes an element, the array A and the index. So index is nothing but the index at which the new element was inserted. Now in this case it will be 31, which is actually, it was 11 because that is where the new node was inserted. So the first step, as we discussed, is to find its parent. So hence in step 1 what we do is we locate the parent, and remember the pattern which we, or the formula we used when we are storing the heap in an array. So parent is located at index by 2, so which means in this case 11 by 2 is 5. So parent was here, so this was 5, and this was 11 at that time. And then what we do is, while parent is greater than 0 in step 2, which means still we have a parent. I mean, it's possible that during this bubble up process we reach the root and there is no more parent. So hence what we do is we check if parent is greater than 0, so which means the parent exists. Then we check if parent is less than the child, which means if the new child that we inserted, or the new index that we inserted, sorry, this should be child, this should be index, so this should be index. So if a parent is less than the index, which means they are out of order, and then we swap those two elements, and once we swap, we now update the index, because notice our element has moved up the queue, up in the heap. So we update index as parent, and we update the next parent as a index by 2, so parent gets updated to the new index, and then we keep doing that till we see this property is satisfied, which means till we find that the parent and the new node is out of order. So this is what is bubble up. Alright, then let's now go ahead and see the next operation, which is the extract operation. Now when we say extract, we essentially mean that we are removing the root element out of the existing heap or the existing max heap. So what is the process? We briefly discussed, but here is it again. So remove the root element, which means we remove the root element and replace it with the last element on the last level. So the last most element that we had in the heap, we just swap it with that, and then once we swap it with that, we have to now, because the root element has changed, so the root element now needs to be bubbled down, so which means the root element might have violated some heap property. So essentially what we do is we copy it with its children, and we see if any of those children is greater than the new root. If any of those children are greater than the root, we pick the largest one of them and then we swap it with the new root, because then only the heap property will be satisfied. Now the max heap property states that the maximum element should be at the top, and then once we have swapped the new root node, we will repeat this process with the subtree, with that subtree again, till we actually see that there is no more swap is required, or we have reached the leaf, and then we know that the max heap property is satisfied. So let's see it with an example. So let's say this was our heap, and now we want to extract root is 44, which means we want to remove this node 44. So what we do is, as we discuss, first we will replace it with the last element, which in this case is 14. Remember, last element means last element from left to right in the bottommost level. And then what we do is we replace it. We remove 44 and then we replace it. So we replace it, and this is how it looks like in the array. So we will get this, which means 14 will now be the new root, but since 14 is now the new root, the heap property is violated. Why? Because it's a max heap and the element at the top should be the maximum element. Now in this case 14 has two children, 42 and 35, both are greater, and in fact in the heap what should happen is the maximum element should remain at the top. So hence what we do here is we first see the new children that were inserted, the new children of the new node, and then find the maximum of it. Now in this case we have 42 and 35, the maximum of it is 42. So we now need to swap 42 and 14, which means the new node has to be swapped with the greatest element. So we compare 42 and 14 is less than 42, and hence we need a swap. So once we do the swap, now this is how the array looks like. So 42 and 14 are now swapped, and the tree will look like this. So which means 42 now becomes the root and 14 now becomes the child. We have restored the heap property here, but we are still not done. Why? Because 14 might be still violating the heap property with respect to its children, and hence we have to repeat the same process with 14 and its children. So what are the new children of 14? The new children of 14 are 33 and 31, and the maximum of those is 31. So now let's compare the 14 with the new node. So in this case the maximum is actually 33, it's not 31. There is a typo here, and what we do is we compare 14 with 33, and then we will replace. Why? Because 33 is greater than 14, so we swap and 33 will go to the top. So this is how it looks like. 33 goes to the top, 33 is now in the second position, and the array looks like this. So we have restored another heap property, but we still need to check if 14 is already in its position. So what we do is we check for the children again of new children of 14. New children of 14 are 10 and 26, and the maximum of those is 26. Now let's compare 14 with 26, and in fact 14 is less than 26, which means there is another swap required, and we need to make 26 as the parent of 14. So we will replace it, we will swap it, and then the new array will look like this. So 26 will replace 14, and the tree will look like this. So finally looks like we have placed the 14 in its place, and the algorithm will end here because 14 now no longer has any children. So hence we say we are done. So we are done with the bubble down operation, and this is the final array that we have. Alright, cool. So we are done, and let's now see this algorithm in action, which means, this algorithm steps. So here is a bubble down. So the bubble down method takes a and the root location. So the root location in our case is basically just 1. In some cases where we need to bubble down the element in a subtree, their root location might vary, but this is how it looks like. So this procedure, what it does is it bubbles the root element at the root to its position in the binary heap. So the first step is to get the new child of the root. So first we have L child, which is the left child, is located at a star 2. Now this is based on the pattern and formula we devised earlier, and right child is located at 2 times root plus 1. So L child will be 2 star 1, which is 2, and right child will be 2 star root plus 1, which is 3. So we have left child and right child. Now we need to check whether the left child falls within the range, so which means if the left child is a valid element in the heap or not. So that's why we check if L child is less than the length, which is true in this case, in the first case, and then this is what we do. So what we do is, in the first few steps, we just find we find the maximum. In the step 4 to 7, we find if there is a maximum of the children, and if those children are greater than the root. Now here is what we do to check that. We use a current pointer which points to the root, and first we compare the root with its left child, or the current with its left child. So if the left child is greater, then we say the current is actually the left child. Similarly, we check if the right child is valid and the right child is greater than the current node, which means the right child is greater than the current. So what we do is we assign current as the right child. So during this process, what will happen is current will point to the maximum of the 3 elements, the root, left child and the right child. So what do we do in step 8? In step 8, we check if the current has changed. So which means if the current is not root. If the current is root, which means root is already in its position, so there is nothing to be done. We just return, else return. But if my current has changed, which means either my current points to the left child or the right child, which means either one of those children is actually greater than the root, what we do is I swap those 2 elements. So I swap current and root. So once we swap the current and root, now we have to move to the new subtree. Now to move to the new subtree, what we do is we assign root as current. So which means now root points to the new child whichever was replaced, and then we assign new left childs and right childs, which left child will point to 2 times the root, 2 times the new node, and right child will point to 2 times the new node plus 1. And then the while loop again executes, which means we go to the subtree and we do the bubble down process again. So we do the swapping again till the element actually reaches in its position. Alright, cool. So this was extract root. So now go ahead and let's move ahead and then see the next operation, which is search. Now search in a max-heap behaves something like a very linear search in algorithm, in linear search in an array, not algorithm. So to search for an element in a max-heap, what do we do? So we just simplest strategy, compare it with root first and check if the element is greater than the root. Now it's a max heap. If the element we are searching is already greater than the heap, we know the element is not present in the heap because the root node is the maximum in the heap. So we just return not found. If the element is equal to the root, which means if we have found the element, then we just return the index of the root or the new the root element, and then we are done. But if both are not done, then we have a left subtree and the right subtree. So what we do is we recursively search the element in the left subtree and right subtree, which means we call the search operation with the left subtree as a tree and then pass the left child as the root to the search method. Similarly with the right tree. So let's see an example, an intuitive example. Let's say here is a binary heap which we have, and we need to search for an element 26. So notice where 26 is present. 26 is present somewhere in the heap, it's present at the down. But how do we start? First we will compare the root. So notice root is 44, 26, the 26 is less than 44, which means there is definitely a place where 26 might be present in the tree because 26 is less than 44. So we move to its left subtree. In the left subtree we will be hit with 42, which is its root, and then we'll compare our search the number with 42. So we compare 26 with 42, and 26 is less than 42, which means it's possible that 26 is present in its left or right subtree. So we'll go to its left subtree again. We'll compare 26 with 33, and we will say that 26 might still be present. We'll continue our search. Next we will go to the left subtree of 33, which is 10, but here we see that 26 is greater than 10, so which means 26 is definitely not present in any of the subtrees of 10, and in fact 10 is also the last element in its own subtree. So since 26 is greater than 10, we know we have to end our search again and return. Now once we return, we'll return back to 33, but in 33 we will see that we are done with the left subtree. We'll go to the right subtree of 33, and when we go to the right subtree of the 33, we will actually see that 26 matches with 26, and hence we will return here. So our search is complete and we will just complete the search. Alright, cool. We'll see another example where the element is not present, but before that let's first see how the search algorithm looks like, or how the search process looks like. So search procedure takes the array A, the root node, which means the node of the subtree because it's a recursive call, and then the key or the element that we are searching for. So here is the algorithm. So first step is to check if root is less than a dot length, which means if we are in the subtree or not. So you know, the element exists or not. So if root is less than a length, then what we do is we'll compare. The first step is to compare key with root, so which means we'll check if the root itself is the key. If that is true, then we'll just return root. We are done. Then we check if key is greater than root. Now if key is greater than root, there is no need to continue our search further because our key is already greater than the root. It will definitely be greater than all the elements in the root, so we just return -1. Now here -1 indicates that the element was not found in the binary heap. Alright, now if both the conditions are not true, which means the element or the key is less than the root, we have to continue our search, and hence first what we do is we continue our left search. So we will continue search in the left subtree. So we'll just recursively call this method search with a 2 root and then key. So 2 root, remember it, this is basically the left subtree, the root of the left subtree, and then we'll just call, and then the value is returned in index. Now if index is -1, so which means we have not found the element in the left subtree, then we will search for the element in the right subtree. Now the right subtree, what it does is it calls the same recursive call with the right child as the root of the right subtree, which is 2 root plus 1. And finally, once we are done comparing or searching for left or right, we return the index. Now if index was if the element was found, then that the index of the element will be stored in index, and hence we return. And finally, if we notice that there is root is greater than a dot length, then we just return -1, saying the element is not present. Alright, cool. Now let's see this algorithm, apply this algorithm to an example. Now in this case we have this binary heap, and let's say we need to search for 37. Notice 37 is not present in the heap, but let's see how this algorithm or how the recursive calls are made. So the first step, as we know, we go to step 1, we check if root is less than a dot length, which is true because root in our case is just 1. So 1 is less than a dot length. So let me actually number these nodes so that it will be easier. So this is 1, this is 2, this is 3, 4, 5, 6, 7, 8, 9, 10. So in the first case we have root as 1 and the key that we are searching as 37. So first step will be checked 1 is less than a dot length, definitely, because 10 is the length of a. So then next step is to compare key with root. So 37 is not equal to 44, so we won't execute step 2. Then we go to step 3, 37 is greater than 44. No, 37 is not greater than 44. So 37 is actually less than 44, and hence we'll go to step 4. Now in step 4 what we do is we search a 2-star root key. Now 2-star root will be 2 and this will be 37. So which means we will make a search to the array A starting at node 2 and which is 42, and then search for key 32. So that's what the first recursive call does. Now when this recursive call is called, what happens is the same method is called with different values. So which means the root now changes to 2, and what we do is we perform the same operation. Step 1, step 2 will fail. In step 3 will also fail because 37 is less than 42. So we'll come back to step 4 again, and in step 4 what will happen is we will again call the search method or recursive method with its child, left child, now which in this case is 2*2, which is 4. So we will call search 4, 32. So what it will do is it will make the next recursive call to the search method with 33 as the root. Now same thing will happen. Now when this happens, what will happen is 3 will be passed as the root. So no, sorry, 4 will be passed as the root. So we have 4 here, and what we will do is this condition will succeed, but 4 is not equal to key is not equal to root. Key is 37 and a root is now 33. In fact 37 is greater than 33, so step 3 will succeed, which means key, which is 37, is now greater than 33. And since step 3 will succeed, it says there is no need to go further because my value 37 is already greater than 33. Definitely it will not be in its subtree, so we'll return back here. And hence what we do is we return -1 in this case, and then -1 will be returned. Now what will happen is it will go back to the previous recursive call that we had. Now in the previous recursive call we had this as 2, and we had this as 2. Let me just put it down here. So this was 2, and my left subtree call here, this would have returned -1 because 37 is greater than 33. Next what happens is we go to step 5 where we check index is equals to -1, which means the element is not being found. So find the element in its right subtree. So search a 2* root plus 1 and key. So this 2* root plus 1 is 5, 2 into 2 plus 1. So hence search will now be done in the right subtree over here. And when this recursive call is called, 37 will be compared with 31, and we will also find that 37 is greater than 31. So which means we have to again return -1 over here. So what will happen is this will also return -1, and then we will return -1 to the previous call. So the previous call was search 1. So in this case root was 1. So I'll just rub here. Root was 1, and in this case both its children return -1, this returned -1, this returned -1, and we can't do anything, which means the element is not found, and hence we'll return -1. So that's what we are doing here. We return -1 to the main call and to the sorry, this was 2 here, it's not 1. So in case of 2 we return -1, and then we will go back to the next recursive call, which was the original, the first call which we had made for the search. So the first one is one here, and in this case the left subtree, which is the search, returned -1. So in this case we have to search the right subtree. Now the right subtree will be this side, and in the right subtree what will happen is 37 will be called with compared with 35, and 37 will be greater than 35, and hence there is no need to continue further. So even this search will return -1, and finally we will return -1 to basically we'll return finally we will return -1 out of the whole procedure. So this means that 37 was no longer found in the heap. So that's how it is. So I believe it was a little complex, but yeah, if you just trace it down through the steps, you'll see that it becomes easier. So this is the final value return, which is -1, and let's now move ahead to the delete, which is the last operation we have. Now the delete operation is probably the complex ones operation, but it uses a combination of bubble up or bubble down. So delete an element of the array. So the step is to just replace the element with the last element in the bottom level. So which means the same way we did for the extract max, and then now what we have to do, we have to see, because the new element has been inserted, some element has been replaced. Now we need to reorder the heap or restore its property. So first what we will check is we'll check the up property, which means we'll check if its parent is less than itself, or if the element is greater than the parent. Now if that is true, then we will bubble up to restore the max-heap property. Otherwise we will compare it with its children to see if any of its children is greater than itself, and in that case we have to do a bubble down to restore the property. And notice it will be either one of these, either we have to bubble up or we have to bubble down. It's not that both have to be done. So depending on the value of the node as compared to its parent and children, we have to either do bubble up or bubble down. So let's see an example in this case. Now let's say we have the same binary heap which we had, and we need to delete the node 35. So the first step, remove the lastmost element, or replace 35 with the lastmost element, which is 14, and proceed ahead. So this is what we do. We have replaced 34 with 14, not 34, sorry, 35 with 14. So once we replace 35 with 14, the heap property is now destroyed. So what we need to do is we need to do a comparison on this side as well as to its child to see which side we have to restore. So first what we do is we check the parent property. So which means we will check if the parent, if with respect to the parent, the heap property is already present. So let's do that first. So first step is 14 is checked with 44, and in fact 14 is less than 44, which is cool because that's what it should be. It should be less than its parent, and hence the parent property is already present. So there is no need to bubble up. So we just stop here and then we are done. Cool. So there was no need to bubble up. So the array remains the same. And now let's see if the lower property is satisfied, which means if the children are less than the new node. So the children, so let's see the bubble down property. The children are 19 and 27, and notice actually both of them are greater than 14, and hence we have to do a bubble down. In bubble down, what we do, we find the maximum of the children. So in this case, maximum of 19 and 27 is 27, and then we'll compare that with the element, which is 14, and we find 14 is less than 27, which means the heap property is destroyed here. So we need to do a swap. So we swap it, and then we will have 27 in place of 14 and 14 in place of 27. So what this will result is, this will result in this tree, and I think we are done here because 14 has no more children, so there is no more bubble down process that needs to be followed. All right, so 14 is placed at location 7, and now let's see this this algorithm or this procedure in steps. So delete, what delete does is it takes the a as the array and the index at which the new element was, or the element at which was replaced, or the element which needs to be deleted. So the first step is to actually replace it with the new element, so which means this is what we did here, a index. So the element, in our case 35, was replaced with the element which was 14. And then what we do is, for the new element, first we will see the bubble up property. Now for the bubble up property, we have to first calculate the parent. So parent, as we know, is located at this formula, index by 2. So we'll first compute the parent, and then we check if parent is valid, which means a parent is not negative, which means there is at least a valid parent, and if the parent is less than index, which means if the parent is less than the new node or the node that we replaced. And if that is the case, then we need to do a bubble up, which means we need to bubble the element up towards the root. If that is not the case, we are sure we need to do a bubble down. Either of them is always true, because in this case what will happen is there will be children, and those children will be greater than this node, and they will need to be, and hence this new node will need to be bubbled down towards the leaf. So this is how the delete process looks like. So because we had already defined the bubble up and bubble down methods, this delete process now looks very easy, or very simple, or it was very short. Alright, cool. So we are done with the last most operation, which was the delete operation. Now let's see how these operations of binary heap look like in terms of complexity, in terms of time complexity. So we will first analyze the bubble up and bubble down procedures, because they are the core of at least 3 of these operations. So here is the bubble up procedure. So in the bubble up procedure, we have one while loop which checks if parent is greater than 0, and then parent is recursively assigned to index by 2. So what happens here is, essentially, after we have added the new element to the end of the array, we recursively go in the tree, we go up one level, and then we see if we need to bubble up the new element, and we do that till the element is actually positioned in its array. In the worst case, what happens is, if the length of the tree is n, or in other words, if the length of the tree is index, so this process actually runs through log index time. So if we say that the tree length was earlier n, or which means if we had an array A of length n, which the new element might need to be swapped, at least might need to be swapped in worst case log n times. So hence the bubble up process actually takes order log n as a worst case. Now let's see the bubble down process. So in the bubble down process, which looks like this, we have bubble down process takes A and the root element, and we have a loop in which we calculate the L child or the left child, and the left child starts from the root and then it goes till the end of the array. And every time we perform certain operations, what we do is we swap, we make current as root, and root now points to the current. After current points to one of the children, current points to one of the children, and the left child is again assigned to the child of the root. So which means we are essentially traversing down the binary tree or the binary heap, and it ends when we are done, or the element is actually positioned in its position, or the element has been positioned in its position. But in the worst case, we will assume that the element traveled from the root to one of the leaves. So in this case, order log n times there were comparisons done, and hence in this case also comparisons is log n. So in short, in summary, bubble up is log n and bubble down is also log n. When we are saying it's the worst case, in the best case probably there was only one comparison needed in bubble up and also one in bubble down, but we are considering the worst case in this case, or even the average case. Even in the average case it will be log n. Alright, cool. Now let's see each of these operations and then find its time complexity. So the first one is the insertion. If you remember, in insertion what we did is, once we added the new element, we do one bubble up operation. So which means it's only once we have to bubble up the newly added element to its position. So this is order log n, because one bubble up means its bubble up we know is log n. Similarly, extract max, in which we replace the root and then we had to do one bubble down, which means we bubble down the root element to its position. This is also log n. Now the third one, which is search. Now in this case what happens is, there was no efficiency done compared to array. So essentially what we did is, we compare it with the root. In the best case, we know if it's greater than the root, we exit, but otherwise we have to continue and search in the left subtree and also search in the right subtree. So in the worst case, we end up comparing with every element in the array, which is possible, and hence it's hence it is n. So it's not order log n, because we have to compare every node in the array or every node in the tree. So the length of the tree or length of the array is n, and hence the search operation is order n. So this is similar to a linear array. And then finally the delete operation. Now in delete operation what happens is, we have either one bubble up after we have replaced the node, and then we check if we have to do a bubble up or bubble down. We do either one of it, and once we do, either we bubble up or bubble down, and hence this is also order log n. So in short, insert, extract and delete are log n, whereas search is order n. Alright, so that was all about the binary heap video, and I think we are done here. I hope this explanation for the heap helped. If you have any questions, comments or clarifications, make sure to post it in the video, and I'll definitely try to address them. So finally, before we end, here is an exercise for you guys. So all this exercise is based on the learning so far for heap which we did. So first of all, build a max heap by inserting the following elements in the sequence. So initially assume that the heap contains nothing, and we start inserting 12, then 10, then 9, and then so on. Next, search for the following elements in the heap, 8 and 7, and see how the recursion happens, how the comparison happens, and how many comparison happens, and whether these elements are present in the heap or not. Third, delete the following elements in the heap structure. So delete element 9 and delete element 1, both are present. So make sure when you are deleting the element, follow the process which is bubble down or bubble up or whatever is required, and then go through the steps one by one, and then get the final heap which now has the heap property satisfied. Next, the last one is, once you have the new heap structure after the operations, now extract the maximum element from the remaining heap. So extract root and then output it and reorganize the heap again, which means perform the bubble down and then repeat this process. So remove the next element and then bubble down and keep doing it till the heap is empty. So once you have the elements that are output, see the elements and see if you have found out a pattern in the outputted elements. So alright, cool. So those were the questions from this video. If you have any clarifications, and if you even want to know solutions to any of these and you're not able to proceed with, comment on the video and I'll definitely address it. Alright, thanks guys, thanks for watching another video from our channel. Please like, subscribe and comment. Bye.